Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So today we are going to discuss on the module Quantum Confinement Effects under the paper Nanoscience and Nanotechnology first. So students, let us see what we are going to discuss in this module. First, we will discuss the various types of nanostructures. Second, we will discuss about the quantum confinement. Third, we will discuss about how a particle moves in the potential well. Lastly, we will discuss about or we will derive the energy and the wave function of a free particle. So students, let us start with the basic introduction about the module. The most popular term in the nano world is quantum confinement effect, which is essentially due to the changes in the atomic structure as a result of the direct influence of ultra small length scale on the energy band structure. The length scale corresponds to the regime of quantum confinement, ranges from 1 to 25 nanometers for a typical semiconductor groups of 5th, 3rd to 5th and 1st to 6th, in which the spatial extent of the electronic wave function is comparable with the particle size. So, as a result of these geometrical constraints, electron feels the presence of the particle boundaries and respond to the changes in particle size by adjusting their energy. This phenomena is known as quantum size effect. Quantization effects becomes most important when the particle dimension of a semiconductor near to and below the bulk semiconductor Bohr exciton radius, which makes the material properties size dependent. So when the particle size approaches the Bohr exciton radius, the quantum confinement effect causes the increasing of the excitonic transition energy and blue shift in the absorption and luminescence band gap energy. In addition, quantum confinement leads to a collapse of the continuous energy bands of a bulk material into the discrete atomic like energy levels. So, a quantum confined structure is the one in which the motion of the carriers, electrons and holes, are confined in one or more directions by potential barriers. Semiconductor nanostructures. Among the semiconductor systems, the three important generic types of nanostructures are referred as quantum wells, quantum wire or a nanowire, quantum dot or nanocrystal, colloidal quantum dots, etc. Alternatively, these structures are also referred as the low-dimensional systems and possess a given dimensionality. Specifically, they are called as two-dimensional 2D systems, quantum wells, one-dimensional 1D systems, quantum wires, zero-dimensional 0D systems, quantum dots, where the stated dimensionality reflects the degrees of freedom of carriers, that is, electrons and holes in the material. So, this shows a schematic of, now if we consider a quantum well, which is a thin slab of semiconductor sandwiched by an insulator on either side, when its thickness becomes narrow along the z direction of a Cartesian coordinate system is shorter than the characteristic length of electrons and holes in the material, carrier confinement occurs. At the same time, since the dimensions of the material along x and y are much larger than the critical length, carriers experience no additional confinement effects. They therefore possess 2 degrees of freedom. Thus, electrons and holes in quantum wells experience 1 degree of confinement and 2 degrees of freedom. Next, let us discuss about a quantum wire. A quantum wire or a nanowire is a semiconductor elongated along a single direction with two associated orthogonal dimensions that are much narrower. Carriers in quantum wire possess 1 degree of freedom and 2 degrees of confinement. Let us now discuss about the quantum dot. Quantum dot structure is narrow along all the three directions of a Cartesian coordinate system. Quantum dot is a small semiconductor particle having its radius smaller than the characteristic de Broglie wavelength or Bohr radius of carriers in the material, and as such, carriers do not possess any degree of freedom. Students, let us discuss about the quantum confinement. In nanocrystals, the electronic energy levels, they are not continuous as in the bulk, but they are discrete, that is finite density of states, because of the confinement of the electronic wave function to the physical dimensions of the particle. This phenomenon is called as the quantum confinement, and therefore nanocrystals are referred to as the quantum dots. As the material becomes confined to the density of states changes. So in the confined direction, you can think of the carriers as the particles in boxes, and 0D corresponds to a quantum dot. So if a bulk metal is made thinner and thinner until the electrons can move only in 2 dimensions instead of 3, then it is 2D quantum confinement. Next level is a quantum wire. Ultimately, we have a quantum dot. Let us now discuss about the quantum confinement in detail. This figure shows the quantum confinement causes an increase in the energy difference between the energy states as well as the band gap. Both these effects strongly influence the optical and electronic properties of the materials at nanoscale. Now, if the diameter of a molecule is reduced such that it becomes comparable to the de Broglie wavelength of electron wave function, it experiences quantum confinement effects. The electronic as well as optical properties of such small materials considerably differ from the properties of bulk materials. If the dimensions of the confining structure are very large in comparison to the de Broglie wavelength of the particle behaves like a free particle. So, in this state, the energy states are continuous and the band gap is at its original position. Nonetheless, when the dimensions of confining structure are decreased down to nanoscale, the energy spectrum does not remain continuous and becomes discrete. Consequently, the band gap exhibits the size dependence and eventually causes a blue shift in the emitted light as the particle's size is decreased. In particular, this effect demonstrates the consequences of confining the electrons and electron hole or the excitons within a dimension which approaches the critical quantum limit, often termed as the exciton Bohr radius. In this view, a quantum dot confines in all the three dimensions, a quantum wire, nanowire confines in two dimensions, and a quantum well confines only in one dimension. The corresponding structure are also termed as the zero-dimensional, one-dimensional, and two-dimensional potential wells, respectively, with regard to the number of dimensions in which the confined particle has freedom of movement. Let us now compare the microstructure versus nanostructure. So, in the case of microstructure, we apply the semi-classical physics, and in the case of nanostructure, we apply quantum mechanical concept. Electron's nature is particle-like and wave-like in microstructure and nanostructure respectively. Energy is continuous in bulk and discrete in nanostructure. Current is also continuous and quantized in nanostructure. Decision is deterministic and probabilistic in microstructure and nanostructure respectively. Fabrication: in microstructure it is microfabrication and in nanostructure it is nanofabrication. Surface to volume is small and it is very large in microstructure and nanostructure respectively. Packing is low in the case of microstructure and it is very high in the case of nanostructure. Understanding through quantum mechanics. Nanostructured materials demonstrates electronic and optical properties which are strongly influenced by their size as well as the shape. The theoretical simulations have been used to investigate the size and the shape dependency of the material's properties. This has led to the developments of various novel structures such as quantum dots, which exhibits strong quantum confinement effects. So these threshold evaluations, they are based on the fact that an exciton behaves increasingly as an atom when its surrounding space becomes smaller and smaller. So an excellent approximation of the behavior of an exciton is three-dimensional model of a particle in a box. So the solution to this problem suggests that the energy states and the dimensions of the space, they are related by a pure mathematical relation. So the energy of the states increases as the volume or the dimensions of the available space are reduced. So this figure shows the differences in the electronic energy levels and the band gap of the nanomaterial and its bulk counterpart. So the relation between the energy level and the dimension spacing is given by psi nx ny nz equal to the root of 8 by Lx Ly Lz multiplied by sine nx pi x by Lx sine of ny pi y by Ly multiplied by sine of nz pi z by Lz. And the energy is given by E nx ny nz equal to h cut square pi square by 2m multiplied by nx by Lx the whole square plus ny by Ly by the whole square plus nz by Lz the whole square. So the variation in the properties of the materials at nanoscale can also be understood as in bulk materials, the surface controls most of the macroscopic properties of the material, whereas in nanostructured materials, the surface atoms or molecules do not follow the expected configuration in space. Consequently, the surface tension is remarkably changed 1 by R2. If the shape of the confining structure is assumed to be spherical, we obtain R1 equal to R2 equal to R. Now, by solving the Young-Laplace equation for the new radii R in nanometer, new delta P gigapascal can be estimated. As can be observed from the above relation, delta P scales inversely with R. So as a consequence, smaller the R, greater is the applied pressure. The increased pressure at the nanoscale dimensions causes strong forces towards the interior of the particle. Effect is more pronounced at the surface. Such aberrations at the surface results in modified interatomic interactions and band gap at nano dimensions. So this figure shows the classical mechanic explanation employing the Young-Laplace law to provide the evidence on how pressure drop advances from scale to scale. Quantum mechanics is used to solve the model systems that illustrates the confinement of the particles, example an electron, in 1, 2 or 3 dimensions. So these are referred as particle in a box, particle in a cylinder, particle in a sphere. So the wave functions and energies of confined particles can be obtained by solving the Schrödinger equation. So the difference between these systems lies in their boundary conditions. These constraints dictate where the particle can and cannot be and reflect the underlying physical geometry and restrictions of the system. This is why one often refers to a box, a cylinder, and a sphere while modeling the quantum wells, quantum wires, and quantum dots, since these are their natural geometries. Therefore, minus h cut square by 2m d square psi by dx square equal to E psi. So in order to solve this equation, rearranging the equation gives d square psi by dx square equal to minus 2me by h cut square multiplied by psi, and let k square equal to 2me by h cut square, where k is called as the wave vector, which is related to the particle's momentum by p equal to h cut k. Also, de Broglie wave-particle duality, that is lambda equal to h by p, can be written as p equal to h by lambda. So multiplying the numerator and the denominator by 2 pi, it gives p equal to h cut by lambda by 2 pi. This is just p equal to h cut by 1 by k, leading to p equal to h cut k. So on substituting k square into the above equation, the following second order differential equation is obtained, that is d square psi by dx square plus k square psi equal to 0. So it has general solutions involving the linear combinations of plane waves, that is psi equal to a exponential iota kx plus b exponential minus iota kx, where a and b are constant coefficients which can be determined. That is, it has periodic boundary conditions, also called as Born-Karman boundary conditions. The following relation applies: psi x equal to psi x plus lambda, where lambda is the wavelength or the period of the wave. So using our previous solution for psi, we then have the following relation for the first term, that is a multiplied by exponential iota kx equal to a multiplied by exponential iota kx plus lambda, which is reduced to a exponential iota kx multiplied by exponential iota k lambda. A similar equality applies to the second term. Thus, for either to be true, exponential iota k lambda must be equal to 1. Since the Euler relation says that exponential iota k lambda equal to cos k lambda plus iota sin k lambda. So we have k lambda equal to 2n pi, where n is 0, plus minus 1, plus minus 2, plus minus 3, so on. We thus find k equal to 2n pi by lambda as constraints on k that arises due to the periodic boundary conditions of the system. So we can express the wave functions as, since there are no constraints on A or B, we are free to choose a solution. For convenience, let B equal to 0. This gives psi x equal to A exponential iota kx as the free particle wave function. And the corresponding energies are given by the accompanying energies are found by using the definition of the wave vector, namely, since k equal to root of 2me by h cut square, we find that E equal to h cut square k square by 2m. This reveals a parabolic energy dependence on k, which is systematically shown in this figure. So students, let us summarize what we have learned in this module. First, we discussed the various types of semiconductor nanostructures. Second, concept of quantum confinement was discussed in detail. Third, the potential well system along with the wave function and energy of the particle in this system was discussed. Lastly, energy and wave function of a free particle were derived in detail. Thank you.